running start. Okay, so I said 3 laws. Okay, and actually, this is one of 3 of Kepler's laws. So Kepler was a student of Brahe. Yeah, and that's the only thing I might, broadly ask you kind of general questions about that sort of history. Okay. So, and I will ask you, and I think you might have a homework question that's going to be due next week to summarize his 3 laws. Okay, so his first law was the shape of the orbits of the planets, including ours, ellipse. Okay, and this is kind of another look at what all that means. And actually, this slide, I'll put all the builds up here. This is what I kind of put on the other slide, isn't it? That if the sun, and it is kind of off-centered as the planets orbit it, sometimes we're closer and sometimes we're farther away. When we're closest, we call that perihelion. And when we're farthest, we call that aphelion. Okay. Any questions about that? Oh, so here's where I get to say, if you're like me, you want to go visit that location. Like, what's here? And as far as I know, there's nothing over there. But it looks like another sweet spot. There could be something interesting. Okay. And do you guys remember, because we covered this in the last chapter, what time of the year are we closest to the sun, perihelion? It's actually the opposite for us. Our summer, we are farthest. So.
But we're facing it at a different time, so it's...
The angle is, yep. So, in the last chapter, we assigned dates of actually January 3rd, I think, for perihelion, and July 3rd, right before Independence Day, for when we're furthest. And so, yeah, we talked about seasons and such, and remember, when we're having summer, the other hemisphere's having winter.
Which is where you would think that the closer you are to the sun would be summer.
Mm-hmm. But that distance doesn't, it is interesting. I like it. Okay. So, I know it probably doesn't look like it, but this actually, his second law is, I'll put it this way. Which planet, Earth or Mars, goes faster when it orbits the sun? Earth, yeah. Earth goes faster when it orbits the sun, exactly. And this doesn't look like it, but that's what this is saying. Okay. Oh, no, this isn't. Sorry. Oh, let me go back. All right. Forget that I said that. Erase. Here's the deal. Pick a planet. Pick Earth. And when we are coming to our closest spot to the sun, the gravity between the Earth, that gravity that the sun is imparting on the Earth makes us go a little bit faster. So if I were to go, if I were to kind of sweep my hand around, it would go like, I'm going like this. I'm going, oh, sorry. I know with that pencil. I would go, okay, you get the idea? Okay. Whew. Okay, so we go faster at perihelion and slowest at aphelion. It's a gravity thing. And because of that, if, and I'm going to kind of pick on this slide a little bit more, okay, if we talk about, let me change the color of my pencil, just because I can. As the Earth orbits the sun, if we talk about this location and this location as time A and time B, okay, what this is saying is we could talk about this location, and this location is being C and D. Okay. So here's the deal. The time segments, A and B, same as time segment CD. Okay, because we're going faster at A and B, aren't we? Okay? So the whole equal area thing looks like this. The equal area thing, I'll pick a different color, one more color, just because I can. The whole equal area thing says that this area is equal to this area. Okay, that's it. And why? Because we go faster when we're at perihelion and slower when we're at aphelion. And notice how the areas are. The areas actually go back to the sun. Okay.
So that explains how come our days are longer in the winter, or in the summer and shorter in the winter.
No.
We're going fast. Well, it kind of makes sense.
Oh,
Because you said on over here is when we have winter, right?
interesting.
And you're going faster through that
I
time
have to
frame.
think about that.
So your days are shorter.
Yeah, but we have to think hemispheres, so that would mean, what you're saying, I see what you're saying. That would mean like our winters would go faster because we're at perihelion, right? And their summers, southern hemisphere, their summers go faster. I'm kind of liking that. Yeah, because we slow down up there. I never thought of that. It's true. I don't know. I have to think
It's
about
true
this
for
one.
us. I don't know if it would be true for.
Oh, you know what we're missing here, though, is because, pick one more color. Regardless of the distance between you and the sun, okay, whether you're here, regardless of your distance, and this looks kind of exaggerated, I think, to the eccentricity of the Earth's orbit, basically you're getting the same solar energy. I know it looks like we should get more solar energy over here, but that wasn't your point, was it? That your point was we go faster in our orbit.
Yeah, because like it gets darker earlier in the
Yeah.
winter, and your days are longer because your sun's out
I'll
longer
have to
in the
think
summer.
about it. The reason the sun's out longer in the summer because of the Earth's axis is tilted, and as it spins, the higher you are in your latitude, if it's summer in your hemisphere, you get more hours of daylight because of the tilt. Yeah, it's the tilt that gives you more hours of daylight. But I'm not sure you don't have something else here. So I'll kind of look into that. So put another way, if I ever ask you on a test why we have seasons, don't say it's because of perihelion and aphelion. But I do hear what you're saying. Look into that. That was in the previous chapter. Okay. Is this where? Bless you. So did that last slide, I don't mean to drive you nuts, but I'm going to go back one more time. Did this last slide say, yeah, here at the bottom is how I would sum it up. This means that a planet is faster, okay. Because on the next one, I would sum it up, okay. This is the one that I would finally sum up the whole, you guys told me Earth moves faster in its orbit compared to Mars. Oh, here's one for you though. What if you compare Earth and Venus? Who goes faster? Venus, whoever's on the inside track, exactly. And so this is I think kind of a strange relationship. But what Kepler found was that if you take the average distance of the average distance of the planet from the sun, okay, and if you cube that, the time it takes for that planet to complete one orbit and square that, those quantities are equal. So here's the deal then. If you, as you increase distance, that's what A is, what happens to the P? I know it's not a math class, but it also increases. You increase the period. Which, now that I think about it, you increase the period, but you're also increasing, it goes slower. Darn it. It goes slower, but that could be in part because the oval's larger. The orbit of, for instance, Mars is bigger than the orbit of Earth. Okay. Matthew's thinking.
So it takes longer for the,
Remember what 1 AU equals is the distance to the sun, right?
Right.
Okay.
Yeah, the Earth and the sun.
Yes.
Yep.
That's what I was
1 AU.
trying to remember.
Yep. I'm sorry, what did you say?
I'm just thinking, the farther you are from the sun, the longer it takes to orbit the sun.
Right.
Yeah.
Yeah. But to me, you're back to that could be two things. It could be, well, you got a bigger orbit, but we know that they're traveling slower in their orbits too. I don't know. All right. So pretty good. So if what this table does is to emphasize, this is the raw data, okay? And then if you square the period and if you cube the semi-major axis, you're looking for those quantities to be equal. And make that all. So. Okay, my least favorite law. And I'm not necessarily going to, these are some, I think you have to have enrolled in Mastering Astronomy to have access to these. But they aren't that great, trust me. Okay, so we left with Kepler. Cool dude, 3 laws. He took Brahe's data, Tycho Brahe's data. Kepler did, and came up with those 3 laws. And then enters Galileo, bless his heart. And there are, I mean, it's a saga, okay? If you read about Galileo, I'll put all these up. If you read about Galileo, it's kind of a sad story. He had a heart for science, and he also had a heart for his own personal faith in the Catholic Church. So you might kind of picture Galileo with a telescope, kind of holding up a telescope, one of those pirate type telescopes. And Galileo did not invent the telescope, but these some of these things up here, well, some things I'm going to show you, he used the telescope to view in the heavens. He used the telescope to look at the heavens. So even after Kepler's 3 laws, there were still some objections to this idea of putting the sun in the center and having the planets orbit the sun. And here are some of the objections. They make you laugh, kind of, but maybe not. The first one, so if the Earth is moving, okay, when it moves, it's going to leave the air behind. It's okay. And actually, it's called momentum. So actually, because here's, I don't know how to say this, because things can be left behind if all of a sudden motion starts. Things can be left behind. So, because for instance, you know, if I put the paperclip on this and I suddenly go to move my folder, you know, my paperclip's left behind, and that's kind of what their objection was. Okay, but if the paperclip and this is moving at the same speed, you know, kind of accelerate to the same speed, you know, they're going to be good. And the whole thing about the circles, circles are perfect, and so you can't mess with perfection. That is a church thing, okay? And then the third one is the whole, we talked about stellar parallax. Now, the fact that, you know, if the Earth is orbiting the sun, you're gonna see kind of a mismatch of stars making different pictures up there. Stellar parallax. So those three things had to be dealt with still. Okay. So basically, through observations, just kind of like I showed you with the paperclip on top of the folder, okay, he noticed that if an object is in motion, it will stay in motion. So that air associated with the moving Earth will stay moving with the Earth, the same trajectory. Unless something else another force is acting on it. Okay. With regard to the whole circular thing, okay, instead of like he basically said, you know what, we have to get over what we think is perfect, you know, and I think we've come a long way because I would think, you know, I don't know, I just think astronomy is beautiful and it doesn't have to be circular to be beautiful, okay, but his thing was there are imperfections out there. So at the time, using his telescope to look at that there were lunar features, that it wasn't just a nice smooth round thing. I mean, those were boo-boos on the moon, okay? So imperfections. Along those lines, he saw little marks on the sun, we call sunspots, imperfections. Get over it, right? Okay, parallax. So here's the deal with parallax. A few things with parallax. Remember I said Tycho was the kid with the cool toy? Okay, in his data you could actually see that if you were 6 months apart, there was movement in stars that were close. That's cool. Okay, so you do see parallax as the Earth orbits the sun. The other thing is that Galileo used his telescope to actually look at the Milky Way, and like I've been saying, if you use binoculars, you're going to see just tons of stars. So with that sort of new view of kind of that thing that looks like just gas up there actually being stars, he's like, dude, these things are way far away if they look like little misty things, and they're stars. Okay, so that kind of puts some perspective. And one of the things we know about parallax, if you put a tree on a mountain and you move to two different positions, that tree is not going to change. Okay, so he kind of puts some perspective there. Okay, so I think that about did it. But there were a few other things that Galileo is noted for to kind of reinforce this idea that the sun is at the center of our solar system. Bless his heart. I think I mentioned, and I'll just put all this up here. I think I mentioned that Galileo saw moons orbiting Jupiter, because when we were kind of talking about other planets and the fact that there are satellites or moons orbiting other planets. And this is like some of his drawings, that the big round thing is Jupiter, and the things that look like stars actually are the moons. And so he noticed throughout a series of evenings the things which are moons orbiting Jupiter. So that's also kind of like, you know, if the Wanderer can have satellites or moons, you know, you might want to rethink our position, you know. Okay. All right. The other thing he saw is that Venus, see those pictures, kind of the disk going from right to left? The disk, it looks like a full moon, and then a waning gibbous, and then a quarter, and then a waning crescent, and then a crescent, doesn't it? Those are actually images of Venus that he saw. Okay, inner planets will go through phases like this, and this is why. So if we go ahead and leave the Earth still here, and then the brown track is Venus. And we're all about counterclockwise, right? So we just leave the Earth here for now. See how Venus, right at this point, it's kind of like the moon. If I were to ask you, where's the illuminated part of Venus? I bet you guys would tell me it's over here, right? The lit up part of Venus. Well, Venus goes ahead and is orbiting the sun. Now we see a sliver of the lit up part of Venus in this position. Venus goes ahead and continues to orbit the sun. Now we see a half of the lit up part of Venus. Okay? Venus goes ahead and continues to orbit the sun. It's getting close to the sun. But we actually see even more of the hemisphere of Venus. Okay? Are we going to see Venus over there? No. That's problematic. Okay? But as it comes out around the other side, we're going to see it. Gibbous, then quarter, then crescent. Isn't that cool? I think that's neat. So what this does over here, oops, sorry, go back. What this does over here on the left is, this is, no. Remember Ptolemy? Okay, he put the Earth at the center of everything. And so what Ptolemy said was, remember Ptolemy made those little loop-de-loos, okay? Planets orbiting the Earth, which they don't, but they made little loop-de-loos. If you make a loop-de-loo like this, you cannot get the observations. Anytime observations don't match up with your model, something's wrong. So the best he could get is this little loop-de-loo right here. Check this out. You see none of the disk, you see a sliver, okay, and you see none of the disk. You see a sliver. That's not it. Which I know, I don't need to convince you of that. Okay. So I mentioned it was kind of a sad story. He was put under house arrest, and there's like a book written by his daughter, I want to say. It wasn't until 1992 that he was vindicated. You're like, really? So there's definitely some drama there. All right. So to kind of wrap things up a little bit, okay, science or a study or an enthusiasm in something that is not science. Okay. Sometimes that is a little fuzzy. I already kind of said some characteristics of science is that you make observations, and you think there is an explanation behind those observations. Okay, more observations, and whatever explanation you come up with needs to be backed up by your observations and additional observations. Okay, So not all knowledge is science. Just because you know something, you know a fact, doesn't make it science. Okay. So the scientific method, here's some, I'll probably have to have some questions on your test about this. I think you have a homework question about the scientific method. Key terms, as you know, are hypotheses. Okay. Testing is also a key term. Testing, hypotheses. Okay. A hypothesis is the preliminary, what you think, how you think it works. If you are hypothesizing, you are giving your best guess based upon your observations. And so a hypothesis always needs to be followed up by more observations. Your hypothesis needs to stand the test of more experiments. So you have experimental design to see if you're right or not. So based upon observations, you ask a question, form a hypothesis, what you think might be going on behind the scenes. Based upon your hypothesis, then you say, if I'm right, then this must be true. Something else must, if I do this, this will happen. That's your prediction. So prediction then enters like your testing phase. You put together something to test your hypotheses. Notice it can go one of two ways, right? It can be correct or it can be wrong. So if you perform a test and your test fails, okay, something that is inconsistent with your original hypothesis, notice that you have a couple choices. You can, just bail on the whole hypothesis, or you can tweak it and try again. The thing about the scientific community, I mentioned the internet, we live in a very small world. Even before the internet, scientists were like a bunch of little kids in that they get along, but when somebody tries to be bold and come up with an idea, there's people in that same discipline saying, oh yeah, really? Well, let me tell you. So they try to kind of, it's a rugged process, okay, of a hypothesis being tested. So maybe there's some tweaking that needs to go on. Notice that even if you are right, the tests turn up right, you're like, oh, right, okay. I was right, but I'm not ready to publish, okay. There are some interesting, historic times when scientists went to publish when they probably shouldn't. I listened, have you ever heard of cold fusion? So, in a lab, you could, basically take water, I think it was out of water, I don't know. But, so there are times when they didn't do this enough. So, a theory then, and this is I think this is quite clever. It's like if you're playing checkers and you fight and you fight and you fight to get your guy over to the other side, and if it survives without you getting jumped, if you get to the other side, then you get kinged. Okay, so, and then it's a theory. So, if I say chess, I meant checkers, yeah. You get to be kinged. So what ultimately comes out of this pipe is a theory, a scientific theory. So, and I probably have done it too, but when people say that, they don't really know what they're talking about because it's just a theory, I'm like, it drives me nuts. Because if it's come out of this process, it's not a willy-nilly sort of thing. It could still be wrong. Theories can be wrong. But they've got a lot of gusto behind them. So I think there are probably two uses of the word theory. And sometimes they're using it for just hypothesis as a theory.
So it's not really proof. It's not really proven, it's just a theory.
Well, see, to me, and I'll go ahead, I would make the argument that a theory, I say, has been proven to be true. Okay, a theory has been proven to be true. A theory is consistent with the observations and tests and predictions. Okay. Again, it's possible that theories can be shot down and revisited, tweaked, but a theory is not just a guess. So, all right. So is it science or nonsense? No, is it science or non-science? So I kind of mentioned the whole mysticism sort of thing. Science would remove that. Okay, science has to be something that's repeatable, like miracles. Those aren't science. I personally believe in miracles. Okay, we can talk about that later outside class. But science says, for instance, if I drop this, I know what's going to happen. It's going to fall. And science says I can actually, do aerodynamic test of it, and I can take gravity in consideration. We know what's going to happen, okay, naturally. So when I talk, I use the term mysticism, some sort of spiritual intervention. Not to say that doesn't happen, because I think it does, and we can talk about that later. Okay? But that's not science. Those are two different things. Yeah. And then we talked about, let's see, the KISS. This, I think that a good way to look at what I'm trying to say here is that keep it simple. Keep it simple, stupid. Okay. So some would say that when Ptolemy did the planets orbiting the Earth, right, and then they do these little epicycles, and they go on and little epicycles, that made things kind of complicated. And that, when you make your model complicated to try to explain your observations, you are at some point trying to shove a square peg in a round hole. Okay, so, and I mentioned Occam's razor is the keep it simple, stupid, basically. Okay. So in that, there's all sorts of different flow charts. I just showed you one flow chart of the scientific method. When anybody explains the scientific method, they really need to distinguish, they need to include observations, experimentations or testing, hypothesis, and ultimately cycle through several times, and a theory. Okay. Because the thing about miracles, honestly, and I don't know that much about them, although I said I do think they occur, is that you really can't predict for sure when and where that's going to happen. Okay, so here's my little pitch for the word theory. I'm not saying I haven't used it incorrectly, because I bet I have. Okay, so, but in everyday life, I think we usually say, well, it's just a theory, and we should be saying, well, it's just a hypothesis. Let's start that change. When somebody says, well, it's just a theory, say, did you mean hypothesis? Okay. And that would work. Because if it's a theory, okay, then looking at that theory, that scientific explanation from all sorts of different angles, you get the same result. And in astronomy, there are several theories out there that people would like to, but if you look at it different ways and get the same result, then, okay. So I mentioned that scientists are like little kids and they try to, you're wrong. Okay. And I don't know if it's changed much since the internet, but they used to have these journals. So like in chemistry, they'd have a set of magazines, journals, that would be just for chemistry people, hardcore researchers. And so if you came up with something new, you basically be pretty sure you're right, but at some point you would publish in there. And then it would go through I think before publish, you go through a peer, like as in your friends, peers, a peer review process. So, yep, little kids. So when things start when there is evidence that a theory is wrong, then the people in charge of that particular area of science need to get together and fix them. Do you guys have this slide?
Yes.
Okay. Oh. Voila! Any questions?
What was it said, not have failed one?
Not have
The
failed
last slide that you just-
tests.
Crucial test.
Thank you. I think it's funny because we're a couple minutes over, but I shoot for 20 after the hour. And see, like I said, we're just gonna, if you're okay with it, we're gonna bail that third segment. You guys have worked hard. So, I think we're okay for time. So if you're interested in staying for the lab, I'm gonna catch my breath, grab my keys, and kind of head towards the hill. Next week, though, and I will post for Chapter 5, next week make sure you bring Chapter 4 and 5.
Is chapter 4 up yet?
4's not up yet? Oh, goodness. Okay. Yeah, I'll do
I
that.
thought we looked before class.
I'll do that when I go back to my office now.
I think 4 was up when I tried printing one.
Okay, well, we haven't, I looked at what was it, 12:30 or 1 o'clock, I don't know.
Okay. I'll go post 4. Sounds good.